Welcome. I'm Dr Richard Erskine, and this is an online recording of a talk I gave last night on the topic Greening Our Energy, How Soon, on behalf of Nailsworth Climate Action Network. Now, there are lots of opinions that fly around about renewables, and it's very easy to be bamboozled by some big numbers that are out there. So what this talk aims to do is help to clarify some of the issues and to answer a number of questions. It may surprise you to know that in a survey that Ipsos did in August 2022, 8 in 10 Britons were concerned about climate change, and over half thought that the net zero target for 2050 should be brought forward. The questions I want to address in this talk are: could the UK's future energy demand be met by wind and solar alone? And in posing that question, this is not to say that other forms of low carbon or zero carbon energy will not be part of the energy mix. But if I can demonstrate to you that the energy from wind and solar can meet all our needs, then anything else that's included in the mix will simply make that job easier. It won't make it harder. Specifically, in the recent decades, nuclear has met about 20% of the UK's electricity generation, and with the retiring fleet of nuclear reactors, there are new ones already in train, and given the climate crisis, it might be foolish, some would think, to not go ahead with those. So clearly nuclear is going to play some role in the next decades, and no doubt others as well, in tidal, etc. The second question is about opportunities and hurdles on this journey. And the final question, which seems to animate a lot of political discussion, is how soon can this be done? And I want to start by talking about my personal journey. I was very influenced by David Mackay's famous book, Sustainable Energy Without the Hot Air. And it was very forensic in looking at the energy used and hence carbon intensity of different activities, and also analysing how we might get rid of burning fossil fuels to meet our energy needs. Sometime later, I attended the Zero Carbon Britain course at the Centre for Alternative Technology in Machynlleth in Wales. And both these have been very influential in my development in thinking about this. Now, David Mackay's numbers have been reanalysed, if you like, by a recent paper from an Oxford University group. David Mackay felt that getting to 100% renewables would be difficult, if only because Brits are very good at saying no to things, no to this solar farm, no to these new pylons, and so on. He was accused of being pro-nuclear because he felt that we would unavoidably need quite a lot of it. But he replied by saying that he was only really in favour of maths. And his book is still relevant, if you like, in providing a methodology for how we do that maths, if you like, whatever outcome you wish to achieve or believe is the best way forward. But solar and wind, the costs have fallen dramatically in 15 years since David Mackay's book, and British opinion is now firmly in favour of renewables. So I will be sharing some numbers from this Oxford paper that have come up with some really quite interesting conclusions. And not forgetting another Oxford paper which was reported around the world, in fact, which showed that from a global perspective, if we decarbonise energy systems, by 2050, we could actually save trillions of dollars. And really, it was calling for an accelerated rollout, because that actually there was economies of scale and so forth that would come from doing that. Now, people talk about fusion energy, fusion power, which is always famously 50 years away. But we have a fantastic fusion reactor in the sky. It's called the Sun. The Sun deposits about 170,000 terawatts of energy on Earth, which is about 10,000 times more than humanity needs currently. And wait for it, Shell pointed this out in 2005. So those that are sceptical about renewables have to answer this question. Are you really saying that human ingenuity is incapable of harvesting 1/10,000th of the energy that the Sun deposits on Earth? That we cannot use this massive overabundance of energy from the Sun? Before looking to the future, it's worth looking at how the UK is doing. Now, some politicians keep saying that the UK are leaders and kind of infer that therefore we don't need to go any faster. I suppose my answer to this question is, firstly, we were leaders. The Climate Change Act of 2008 was really world-beating, and it was updated in 2050 with the net zero target by 2050. And that was done in 2019. So that was good. But let's look at where we were just a few years back. I'm using a graphic from the Centre for Alternative Technology here, because their graphics tend to be very clear and crisp, but very similar to other reports. What this shows is that the primary energy, and here we're looking at all the energy for for everything we do, that the primary energy was 80% fossil fuels. And fossil fuels, when you burn them, you waste energy. So there's 25% losses from that burning. And the delivered energy, only about 20% of this delivered energy was in the form of electricity. That's in 2017. So what's happened in the last 40 years is that the contribution from coal, if we're looking at electricity generation, has dropped from about 60% to near zero. And this is definitely a great achievement. But in that time, a lot of that has been displaced by gas generation, which is cleaner, but is still emitting carbon dioxide into the atmosphere. And since about the turn of the century, the year 2000, we've seen a rise in renewables, wind and solar, and it's gone from near zero to nearly 40% of the energy mix in electricity generation. So there's a good news story and a bad news story here. So let's start with the bad news, because, I mean, when you look at what the Climate Change Committee say, they say that they said in their 22 report that only 8 of the 50 key indicators were on track, which is a pretty dismal performance. The National Audit Office have said the longer it takes before government finalises its delivery plans, the greater the risk that it won't achieve the ambition to decarbonise power by 2035, or that doing so will cost consumers more. So this is not a great picture. So in summary, the cleaning up of current electricity use has been going okay, but is not complete. And the bigger question is electrifying those sectors of the economy that are not yet electrified. And the two big ones here are transport and heating, but you can add on industry in there as well. I want to spend some time demystifying energy, because some of the numbers around and some of the concepts can be very difficult for those that aren't sort of steeped in energy matters. I just want to overcome some common misunderstandings. Now, the great Nobel Prize winning American physicist Richard Feynman pointed out that actually energy is quite a difficult subject to get your head around. You take a nut bar and it says it's got energy on it, a battery from your electric bike, some petrol in a can. These all have energy, but in quite different forms, and it's like chalk and cheese, shall we say. But for our purposes, we can just use common language to say that energy is any source of usable power. We can certainly observe that it comes in many forms: chemical, solar, nuclear, electrical, etc. And we can also note that it can be transformed from one form of energy to another. So the solar rays that land on the PV panels on the roof are turned into electricity. But as in all of these kinds of transformations, there's energy lost in the process. Now, the distinction between power and energy is quite important, and because sometimes you'll see numbers that are quoted which are really power numbers and sometimes energy numbers. And I'd like to use the analogy really of pouring water from a jug into a container. The rate at which the water pours is analogous to the power, but the accumulation of water in the container, that represents the energy over a certain time. And so a 40-watt light bulb will be quite slow, but after 24 hours, the amount of energy that will be accumulated or drawn down is a roughly 1 kilowatt hour. But 3,000 watt or 3 kilowatt kettle will get to 1 kilowatt hour in a much shorter time, because it's pouring, if you like, faster. And that's really just 20 minutes will get you to 1 kilowatt hour. And if we scale this up to a national level, it starts being even more important to understand the distinction between power and energy. The average UK power demand, let's say, just for illustration, it's 40 gigawatts. Then to calculate the total energy use in a year, we multiply that by 24 hours in a day and 365 days in a year, and we get to 350,000 gigawatt hours. And note the H which has been added to the GW. And 1,000 gigas is a tera, so the shorthand for that is 350 terawatt hours. So we're looking at tens of gigawatts nationally for power, and we're talking about hundreds of terawatt hours for energy. And it's worth just remembering those sort of country-sized units. So when we think about what we need to do, what we need to install and build, it's not as simple as just saying, oh, well, we'll stick up 40 gigawatts of wind turbines, or perhaps a bit more. Because, of course, it isn't blowing optimally all the time, and obviously it isn't shining all the time, the sun, on the UK. So you need to put in a correction factor to allow for that fact, and this is what's called a capacity factor. So in the case of 1 gigawatt of offshore wind, for the UK, the capacity factor is 40%. So we'd multiply 1 gigawatt times 24 times 365 times 0.4 to get you 3.5 terawatt hours per year. With solar, because of our high latitude in the UK, and of course there's night and day as well to add on to that, you've got capacity factor of 10%, and so during a year you will get to 0.9 terawatt hours. Now, given our high latitude and given this difference which you see here, well, why don't we just stick with wind and forget solar? Well, during the summer, the northern hemisphere is tilted towards the sun, and so we are getting a lot of sunshine, and we can have days when we have lots of sunshine but very little wind. And in winter, obviously, we don't get much sunshine, but we often get proportionally more wind. So wind and solar really help each other out here, and you do need both to get to where we want to get to. Now, efficiency is also a key topic when thinking about energy. If we go back to that incandescent light bulb, drawing 40 watts of electrical power, it gets very hot. If you've ever touched one when you've just switched it off thinking it's cooled down, you'll know from the burns. Now, this 40 watt incandescent light bulb produces 400 lumens. Now, the lumens are what we're interested in because we're interested in lighting the room. We're more interested in what job it does, and in this case it's the illumination. But the heat losses are so large that it's actually only 10% efficient. If we can measure the energy in that light and divide by the energy input, we get this 10% figure. But if we go to a LED light bulb, which is also producing 400 lumens, we only need a 6-watt one of those, and so we get increased efficiency because of the much lower heat loss, and the efficiency then rises to 60%. So we have an electrification revolution which didn't start yesterday. There's an apocryphal story about Michael Faraday that he was asked what use is electricity, and he replied, "What use is a baby?" So over the 2 centuries since Faraday and others pioneered electricity and magnetism and its uses, we've seen obviously candles now replaced by light bulbs. The mills that ran on water wheels now run on electricity. Instead of washing things by hand and other strenuous manual labour in the home, that has been replaced by the white goods, the washing machines and so forth that are used in the home. But there have been these holdouts against this electrification, and we'll turn to those now. And of course, the first of these is transport and cars. So in petrol and diesel cars, we have significant losses of energy, even in the most modern, efficient cars. And so the efficiency, the amount of energy that's inherent in the fuel that goes into the car, but the proportion of that actually puts energy to the wheels, which are going to take you forward, is something like 12 to 30%. But with an electric vehicle, it's much higher. We have much less in the way of energy losses. And for the UK, Great Britain, for our cars on the road, we're consuming something like 445 terawatt hours of primary energy from the fuel. But if we all went to EVs would be using 118 terawatt hours, so about 4 times less. For heating, the majority of homes in the UK use gas boilers, and a modern gas boiler condensing gas boiler is quite efficient. You can say it's about 90%, although it's often much less because they aren't always set up right, so they're not always condensing, but that's a whole different story. So we can say that for every 1 kilowatt hour of primary energy in the form of gas that goes into the boiler, we're getting 0.9 kilowatt hours of space heating stroke water heating going into the house. Heat pumps were invented in the 19th century. It's not new technology. And in fact, every home has a heat pump because they have a fridge. Well, let's say the vast majority have a fridge. A heat pump is really a device for moving heat from one place to another place using, the technical term is refrigeration cycle. And in a fridge in your kitchen, it moves heat from inside the fridge to outside the fridge. The heat pumps we now use for heating homes and heating the space and the water move heat, ambient energy from the environment. They concentrate it and then use that to heat the house inside. And people are sometimes puzzled because they say, well, it's cold outside. What if it's -5, -10? -10 may sound cold, but actually it's 263 Kelvin on the absolute scale. So the molecules are still jiggling around like crazy, and there's a lot of energy in there. And the heat pumps are very good at extracting the energy that's in there and then concentrating it and then pushing it inside the house. And they work perfectly well doing that. And so the 1 kilowatt hour of electricity you put in will harvest, say, 2 kilowatt hours of this harvested ambient energy in the environment. And so you get 3 kilowatt hours delivered inside. And so that equates to an efficiency of 300%, although it sounds very odd having an efficiency greater than 100%. So it's generally called a coefficient of performance, or COP, of 300%. I should just add that I'm in a old grade 2 listed house built in 1805 with thick walls and thin windows, and we get to 330%. So as this energy saving trust quote says, heat pumps can heat all housing types of all ages. It simply is not true that you need deep retrofit to heat the house using a heat pump. Of course, insulation is a great idea. It reduces the bills, but it will reduce the bills for a gas boiler and reduce them for a heat pump. There's no special argument for the heat pump, no special reason for a heat pump as compared to a gas boiler. Now, one observation that David Mackay made in his book was that electrification is future-proofing, because once you've got the grid set up and you've electrified the end use, which is very important in this picture, any future source of energy that you want to plug in, you simply plug in. You don't have to change anything. And this is tremendously important. So those that are holding out for fusion power in 50, 100 years' time, well, if it proves for some reason or another to be necessary, fine, plug it in. So how much energy use will there be in the future? This picture, again from the Centre for Alternative Technology, but which is similar to pictures you'll see or figures you'll see in the Committee on Climate Change, show a large reduction in the demand, and the reason for that is because of this efficiency of end use when you go to electrification of end use. So we're not wasting all that energy that we were wasting. You're still doing the same job, you're still getting from A to B, but you're doing it in a much more efficient way. You're still lighting your house with the same amount of illumination, but you're doing it much more efficiently. And so the demand drops, in the case of the CAT report, dropping by 60%. And you get a figure of about 700 terawatt hours per year in this electrified economy, which is very similar to the figure, well, no, it's identical to the figure that's in the Oxford study. But the Oxford study was very conservative. It said, well, there may be additional things that need to happen by 2050. It may be that the world has decided it no longer wants to have so much of its meat produced by cows and stuff. Some people may have gone vegan, but let's suppose they want to eat meat but eat this synthetic magic burgers and stuff. That's going to take energy. We might decide as a world, with the UK contribution in sucking down some of that excess carbon that's in the atmosphere using mechanical means, which requires a lot of energy. So they doubled it. They said we'd go from 700 to 1400. Oh, and we need to add on some more for hydrogen for long-term storage, which I'll come on to in a minute. So we end up with a generous 1500 terawatt hours of energy is the estimate for 2050. Now, is it feasible for the UK to provide that energy? We're a small island, or no. So, well, the answer is yes, and it's ironic because at the start of the Industrial Revolution in Britain, underneath Great Britain, there was enough coal. The energy in the coal underneath Great Britain was equivalent to the energy in the oil discovered in Saudi Arabia in the 20th century. So enormous amount, and that powered the Industrial Revolution. Now, we know from, and you can see from this picture that Britain has some of the best, well, the best wind resources in Europe, and so there's no reason why wind can't power the green industrial revolution. And wind farms can be constructed pretty quickly. Here's a picture of the Hornsey wind farm phases, 2 of which have been built already. It's actually not the construction of them that takes the time. It has been the planning and permissioning and all that stuff. And certainly there's a case for trying to accelerate those planning processes. For those windier areas up north, we don't have the benefit of having such shallow seas, and so there is it's from a cost point of view, it's more advantageous to move towards floating wind resources in those deeper seas further north. So is there space for this 1500 terawatt hours of energy per year? Yes, there is. And it's relatively modest. For solar on land, which is the thing that gets talked about a lot politically, we're talking about 1% of British land to deliver this. And remember, if it's just meeting our current need, it would be 0.5%, which is the same area as the golf courses take up in the UK. So which is more important, greening our energy or golf? I think you know the answer. We can keep the golf courses, but it's not a huge amount of land take up. And the other thing, this little asterisk here, is that we can combine those ground-mounted solar with grazing land, so we're not taking up arable land where you're growing crops, and and it's been shown that you can that coexist. They can coexist, the grazing and the 1%. So there's 30% of our land is grazing, and 1/30 of that land could have ground-mounted solar, and sheep could quite happily graze underneath it. And then we've got fixed offshore, and then we've got floating offshore. And by the way, we won't run out of minerals again either. But that's I guess a separate talk. But there is in the references to this talk the paper that shows this. You often get that what I think is a rather silly argument, which is, oh, we don't have a distribution grid, or we don't have charging points, or we don't have enough heat pump engineers. I mean, every transition in history that's ever happened involves the parallel growth of infrastructure as well as the growth in demand and adoption. So we have to think of, if you like, the electrification of end use, EVs, for example, with the growth in the infrastructure. And you've got to think of these like twins, these siblings here running a marathon together, supporting each other on that race or that marathon. Now, this is a question that often comes up, which is the variability in wind and solar. So although the planet provides 10,000 times as much energy as we need in a particular location, such as Great Britain, it is possible for us to have a situation where we have a mismatch in supply and demand. So we can have situations potentially where supply is way more than we need, but other times when it's less. And there are many ways of addressing this mismatch. One that's discussed a lot by energy geeks is what's called flexibility. For example, demand shifting. You don't need to have all the EVs in Britain charging at the same time. Many EV owners will have a big charge at once a week and then top-up charging during the week. So you spread the demand and you lower the demand curve, so it isn't so peaky because you've managed to flatten it out. You still need the same amount of energy, but it doesn't have to be in such peaks. And you can do that with other uses of energy as well, including heat, for example. So that's great. But it won't. That'll certainly solve the problem of the ups and downs that happen over a 24-hour period, but not necessarily over a week. Another option is to build more than you need. Now, you probably need to do some of that anyway, but to really overbuild, meaning that you don't have a problem when there's a bit of a peak in demand. Now, that's going to involve costs, but since solar and wind's costs have plummeted, this is clearly an option, some level of overbuild. But the other option is storage. So the way this works is if you have some excess wind or excess solar, you use that to take that energy and somehow store it, and then you use that energy when you need it to deal with when there's a lull, if you like, in wind, for example. And this could occur over this might be something that's happening over a few days, or it could be something where you've got an anti-cyclone stuck over Britain for a week or more. And this is a fairly technical point, but it's quite an interesting one, because what studies have shown is that when wind and solar grow in their proportion that they are, if you like, in terms of our energy mix, it's only really when they get above 80% penetration is the word that is used. It's only when they go above 80% that you really get into the need for significant amounts of energy storage or indeed overbuild. So that's encouraging, because we are way off that at the moment. So it's not as though storage is a massive issue at the moment, but it will become a significant requirement to get to 100% wind and solar. And of course, batteries are often mentioned, and like renewable generation, the great thing about batteries is that they can exist at multiple scales. So you can have a domestic setting with solar panels on the roof and a domestic battery, but equally you could have that on a village hall, you could have that in a community, you could have regional, and you could have also grid scale. And when you have these sorts of utility scale batteries, the ones shown here, for example, dotted around the distribution grid or the network, that can relieve pinch points in the network, which would otherwise exist. And then you can have gravitational energy storage. In the case of De Norwig, you have two reservoirs, and water is pumped up to the upper one in the mountain when you've got excess energy from, say, wind. And then when you've got a lull, you then can bring that back. In fact, this was built actually to respond to potential dropouts of PWR reactors, but it's the same principle applies. So this would give you, a massive amount of power. At maximum power, it would last for 5 to 6 hours, which is great, but it's not going to solve the 1 week lull, anti-cyclone situation stuck over Britain. So this is where we get to one of the strongest candidates for long-term storage. According to a recent Royal Society report, they looked at a number of different options, and hydrogen for long-term storage was definitely a strong candidate, if not the strongest candidate. So what they do is you take the excess electricity, you use what's called an electrolyzer to produce hydrogen. You then stick it down a salt cavern, and then when you need energy back, that hydrogen is used with fuel cells typically to then put electrical energy back onto the grid. And the round trip efficiency of that is about 41%, so it's pretty good. And the UK is blessed with lots of potential for salt caverns. In East Yorkshire alone, there's 3,000 potential salt caverns with a potential energy capacity of 366 terawatt hours. And the Royal Society report reckons we only really need 100 terawatt hours really to fulfill that, if you like, that insurance policy, to buy us that insurance policy for energy security. And of course, they did lots of modelling. You put real-world historic weather data in there. You put in demand fluctuations and so forth, and you see whether these can be matched up properly. And they didn't just stop at looking at a couple of months. They looked over 40 years, because sometimes you need to find situations where there was a kind of, if you like, the worst case scenario. So I always find it very amusing that in the press and on social media and perhaps over a pint down the pub, you'll get people saying, yeah, but you get it doesn't always blow, the wind doesn't always blow, as though the engineers and scientists haven't thought about that. Well, of course they have thought about it. That's why they produce reports like the Royal Society report. They think about these things a lot, and plans are being put in place to address that. So I think we need to get back to those questions, and I think the first question, I think you can see I've answered in the positive. Yes, we can get to the goal of powering the UK in 2050 on wind and solar alone. but with the proviso that we need quite a lot of energy storage to go along with that. Now, the details of exactly how this is going to work, that's not set out here. Obviously, there's going to be a transition phase. We're going to be hanging on to those gas turbines for a while longer. There's a whole, phasing out and phasing in, which is going to take time. But in terms of the feasibility of the end goal, that I think has been amply demonstrated. And it's important to point out again, to reiterate, that there'll be many permutations in terms of the planning, and many situations where we need to look at the roles of various forms of energy that will complement, if you like, the big beast, which is wind and solar, but there will be a role for other things as well. So we now come to the question of opportunities. Well, the obvious one is to stop damaging the planet and the ecosystems on which we depend. This is the first opportunity we have, but we also can have clean air in our homes and towns. We can stop being reliant on petrostates and volatile international markets. And we can build a new vibrant green economy based on green energy. I mean, what is not to like? But the hurdles are there as well. We have an ossified planning regime that makes it very difficult once you've built your new wind farm to connect it to the grid, which is a bit silly. So, and we need to unblock deployment of onshore wind and solar. We need reforms in the electricity market to make it possible to then integrate all of these different assets in a much better way than currently. But I think the biggest hurdle of all is the lack of long-term thinking and political leadership at all levels of government. I think if we had that, everything else would just fall into place. It's just been the lack of that has been the issue. How soon? Well, how soon to do what? Because I think it's a poorly defined question. If it's to displace the current gas generating capacity, that's one how soon. But if it's to electrify the end use, EVs and heat pumps basically, being rolled out, and then the generating capacity to meet that demand, we're talking about another how soon, which is obviously going to take longer. But the real how soon for me, which could happen tomorrow or at the next election, depending on which is sooner, is a government committed to fully fledged, mobilised economy, with a plan and a strategy to really go for it. And this isn't. This shouldn't be a party political thing. It didn't used to be. The Climate Change Act in 2008 was a cross-party piece of work. We really need to get to the point where this is not something that is party political. It needs to be a common consensus that we really need to drive for this. And transitions can be very fast. These two pictures of New York streets, 1900 to 1913, going from mostly horse-drawn to mostly petrol cars in the space of 13 years. We just need to stop the missed signals to the public and industry and push on hard. So I want to finish with some final reflections. The lesson for me is it's possible to believe that things are deeply worrying, to worry about the Antarctic ice sheet, to worry about damage to our ecosystems, and that the positive changes are in train, that a sustainable future is possible if we make progressive choices for people and planet. If we think of catastrophe and sit on our hands, all we are then doing is guaranteeing a worse future than might be possible through our inaction and despair, and that's not a great place to be. So I'd really recommend this book, recent book by Ritchie, which is a boost of positive thinking on how to build a sustainable future for people and planet. The second reflection is that system change is much more than mere substitution. If we just take transport, the answer is not, I don't think, to replace 30 million petrol cars with 30 million EVs. It doesn't also mean that we have zero EVs, by the way, but somewhere in the middle there are livable cities, less pollution, obviously, that comes with electrification, but also, not necessarily a car-dominated built environment. And communities need to have a voice in what they want their communities to look like. It shouldn't just be top-down, and I think sometimes some of the aggravation that occurs is because sometimes decisions are imposed without really involving people in how those opportunities play out. And I'd like to return to Machynlleth and the Centre for Alternative Technology, where my journey began. A green transition is essential to save the planet with great technology and the abundant energy. It's a necessary condition to stop burning fossil fuels, but it's not a sufficient condition to get to a fairer world. It's not inevitable that head, hand and heart will work together to create a fairer world. We have to strive to put communities at the heart of everything we do. Renewables offer the opportunity to start decentralizing some of that power. Around energy, for example, has been highly centralized. And we can only do that if we bring communities together on this. And we need, at all costs, to not perpetuate current injustices. And the energy transition could be a great opportunity to help with that. So thank you very much for your time, and I hope you found that interesting. And if you go to Nailsworth Can website, you'll be able to see other things that we've done, which I hope you'll find very positive, and looking to help involve people in positive choices for people and planet. So thank you very much.